You know, the divisibility rules for numbers like 2, 5, or 10 are a piece of cake, right? But what about 7? 7 has this reputation for being the tricky one, the one without a simple rule. Well, today, we're going to pull back the curtain on a fantastic rule for 7 that feels a little bit like a magic trick, but I promise you it is pure, beautiful mathematics. Okay, let's dive in. So, right off the bat, here's a question for you. Take a look at this number, 3,591. Now, without reaching for your phone or a calculator, how would you figure out if that's perfectly divisible by 7? It's not something you can just see at a glance, is it? Well, what if I told you there's a simple, repeatable process to figure this out in just a few seconds? And trust me, it's a really good one. This little trick can turn what looks like a messy, long division problem into just a few steps of super simple arithmetic. So what is this method? Well, it's called the double and subtract method, which is great because that name tells you exactly what you need to do. It sounds a little strange at first, but you're about to see just how elegant it is in practice. Okay, here's the core idea. You take the very last digit of your number, you double it, then you subtract that result from the number that's left over, all the other digits. If that new, smaller number you get is divisible by 7, then guess what? The original number you started with is 2. I know, hearing the rule like that can sound a little abstract, so the best way to understand it is to just do it. Let's make this concrete and walk through a couple of examples together. All right, let's try the number 392. First step, we grab the last digit, which is a 2. Step 2, we double it. 2 times 2 is 4. Step 3, we subtract that 4 from the rest of the number, which is 39. So 39 minus 4 gives us 35. And hey, we all know 35 is divisible by 7, so that means our original number, 392, is also divisible by 7. See? So simple. Okay, that first one was pretty neat. But what happens when the number is bigger, and the result you get after the first step isn't an obvious multiple of 7? Well, that's the real beauty of this rule. You can just do it again and again until the number is small enough to recognize. Let's try it with 7,586. The last digit is 6, and doubled, that's 12. We subtract 12 from 758, and we get 746. Is 746 divisible by 7? I don't know off the top of my head, so we just run the trick again on 746. The last digit is 6, doubled is 12. We subtract that from the remaining 74, and we get 62. Now that we know. 62 is definitely not a multiple of 7, so we can say for sure that our original big number, 7,586, is not divisible by 7. So at this point, you've seen how it works. You have a really cool tool. But if you're anything like me, the most important question in all of science and math is probably nagging you. Why? Why on earth does this weird process of doubling and subtracting have anything to do with the number 7? This is our chance to go beyond just having a trick and really make sense of the problem. It's time to look behind the curtain. We're going to use just a tiny bit of algebra to unmask the logic. And don't worry, this isn't about some dry, boring formula. This is the secret code that makes the whole magic trick possible. Okay, here's the idea that unlocks everything. Any number you can think of can be split into 2 parts. We can call our number n, and we can write it as 10y plus f. Here, f is just the final digit, and y is, well, it's everything else. So, for our old friend 392, f is 2 and y is 39. This simple way of writing a number is the key to the whole proof. So, what this slide does is translate our trick into the language of algebra. It's making a really bold claim. It's saying that our original number, 10y plus f, is divisible by 7 times, if and only if, the number we get from our trick, y minus 2f, is also divisible by 7. That's the hypothesis. Now let's prove it. Okay, let's get into it. Step 1 of our proof, we'll start by assuming our trick works. Let's just say that the result of our subtraction, y minus 2f, is divisible by 7. In math terms, that just means it's equal to 7 times some other whole number. We'll just call that number q. Now for a little algebraic shuffle. We take that equation from the last step, and all we're going to do is solve it for y. We just add 2f to both sides. That gives us a new way of describing y. It tells us that y equals 7q plus 2f. Remember this piece, it's about to become very important. And here's where it all comes together. We go back to our original formula for any number, 10y plus f, but now we substitute that new expression in for y. When we expand that out, we get 70q plus 20f, plus that extra f that was hanging out on the end. And when you combine the f terms, you get 70q plus 21f. Are you seeing it yet? And for the final reveal, Look at 70q plus 21f. Both of those terms are obviously multiples of 7, right? So we can factor a 7 out of the entire expression. And what does that mean? It means our original number, n, is equal to 7 times some other integer, which proves it. It must be divisible by 7. The logic holds up. The trick is real. So that algebra is just beautiful. But sometimes seeing a problem from a completely different angle can really make it stick. This next part is a little more challenging, but it's a fascinating way to think about what's really going on when we perform that subtraction. Okay, this is going to seem a little random at first, but stick with me. Here's the key idea. Multiplying a number by 5 doesn't change whether or not it's divisible by 7. Because 5 and 7 are prime and don't share any factors, if a number is a multiple of 7, then 5 times that number will still be a multiple of 7. And if it's not, 5 times it won't be either. So let's take our number n and multiply the whole thing by 5. That gives us 50y plus 5f. Now we can do something really clever. Let's split that 50y into two parts, 49y and just y. That 49y part is what we can leave out. It's always divisible by 7, so it's not interesting for our test. The part we have to keep is what's left over, y plus 5f. The divisibility of this little piece is the key to everything. And here is where it all connects back so perfectly. In the world of remainders, what mathematicians call modular arithmetic, checking if y plus 5f is divisible by 7 is the exact same thing as checking our original y minus 2f. Think about it. On a clock with 7 hours, moving forward 5 hours is the same as moving back 2. They land you on the same spot. It's two different paths to the exact same destination. So let's zoom out for a second. What have we really done here? We started with what feels like a simple arithmetic shortcut, a little party trick. But by relentlessly asking that one simple question, why, we've journeyed deep into the underlying algebraic structure that makes it all work. So here are the main things to take away from all this. First, you've got a great practical trick in your toolkit now. But more importantly, you know that this trick isn't magic. It works because of the way our base 10 number system is built. Many of these simple arithmetic rules are actually just algebra in disguise. And that's the real lesson. Asking why is the bridge that takes you from just calculating answers to truly understanding what's going on. And I'll leave you with this final thought to chew on. Our entire proof, this whole trick, depends on the fact that we write numbers in base 10, using that 10y plus f structure. But what if we didn't? What if we counted in base 8 or in binary like a computer? How would the rule for divisibility by 7 have to change? That's a fun puzzle and a great way to keep asking why. Thanks for joining me.